This lesson is on solving systems of linear equations. Linear equations are equations with two variables, which we have looked at in the past, and linear equations could also be graphed. For example, a linear equation could be made for the total cost of a cab versus the number of miles you drive using it. And you could have two different cabs with two different linear equations. A system of linear equations will be two of those linear equations considered together, meaning we could look at them both and see, hey, when are they the same? In this case, when you drive 3 miles, both cabs will cost the same amount. So this is a very intuitive way of solving systems of linear equations, and this intuitive way is called solving them by graphing. So let's take a look here. We've got a system of equations is two or more equations considered together. So here's an example. X plus 1 equals 4 and y equals 2x plus 1. How do we find a solution? Well, a solution is an ordered pair which will satisfy all the equations in the system. So for our example here, x plus y equals 4, we could take a look at all of the possible answers to that to be graphed by solving for y so that we can have it in y equals mx plus b format. And if you recall how to graph linear equations, you look at the slope, which is right by x, in this case is -1, which is a -1 over 1, and your y-intercept component was 4, coming from your y equals mx plus b format. So if we start at 4 on the y-axis, we're going to travel down 1 over 1. If you have forgotten this, please review the graphing linear equations video. So here we have a line that represents all the possible points that satisfy this first equation. Let's now graph the second equation in a different color. We've got y equals 2x plus 1. This one is already solved in y equals mx plus b format. Our slope is 2 over 1 that is, and our y-intercept is 1. So we start at 1 and we travel up 2 over 1, up 2 over 1, and so on. This leaves us with a line that represents all the possible points that satisfy the second equation. Now we can consider them together and we can find that the common point, the only common point in this case, is 1, 3. Therefore, that is a solution to the system of linear equation that has been provided for us. In the previous slide, we had the yellow cab and blue cab, so our solution here was 3, 8, which stood for 3 miles costing $8 was the common price for both cabs. Let's take a look at what possible solutions we could have. We just looked at one example where the two lines met at one particular point. Now, imagine if you have two lines floating around on a two-dimensional space. How could they be put together? One way was to have them cross at a random point, AB, and that was the only point where they crossed, so that would be your one answer. What's another way? Well, if you haven't thought of this already, the two lines could have the exact same slope and be traveling parallel to each other. And what happens to parallel lines? That's right, they never meet. So since they never meet, there's never ever going to be a common point for those two lines. Therefore, there is no solution. And what third option did you come up with? The only other way to put together two lines that is different in the sense of these two first examples would be if the line was essentially the same the second time through. If it was just written two different ways, but it's essentially the same line. So it's covering every single point that's common. So you'll notice there's no way for two lines to cross and have two answers, but there is a way for two lines to cross and have all the answers be exactly the same. So in that case, we would say that the solutions satisfy, and you would give your line equation, because the line equation is what explains what that line looks like and what all the points on that line are. We have some further classifications here. One is that a consistent system has a solution. So let's classify these answers. The green boxes would be the answer that you would provide. But is this first system consistent? Well, it has a solution, so yes, it is consistent. The second one is inconsistent. Because it has no solution. And the third one has a solution. It actually has infinite number of solutions, but as long as it has a solution, it is consistent. The next classification is whether the system is independent or dependent. An independent system has different lines. So in the first example, these lines are completely different. Same with the second, but the third, they're the same. So in the first example, it's independent. Second example is also independent. Now the third example is the opposite of independent. It's dependent because these lines depend on each other. So sometimes you may be asked to classify the system, and these are the types of answers you would provide. But when it asks for solutions, you're providing either a point or telling us whether it has no solution, or if it has an infinite number of solutions, make sure to give the line equation, because the line equation will tell you exactly what that line represents. So let's take a look at some examples. In the first example, we want to determine if these 2 points are solutions to this following system of equations. How do we check if a point is a solution? Well, let's consider the first point. In the first point, our x value is -2 when the y value is 4. Why don't we just plug it in and see what happens? If it works for the first equation, then we need to check that it works for the second as well. It's only a solution if it works for both equations. So, let's check it out. 2 times -2 plus 2 times 4, does this give us 4? -4 plus 8 equals 4. Correct. Since it works for the first one, you have to keep going because you need to check if it works for both. 3 times 4, does that equal 10 minus -2? Well, 12 equals 10 plus 2, 12. Yes, it does. So the first example is a solution. Let's take a look at the second example. Plug in 1 and 1. Does this work? 2 plus 2 is 4. Yes, it does. Plug in a 1. 3 times 1. Does that equal 10 minus 1? 3 does not equal 9, therefore it doesn't work. As soon as it doesn't work for one of them, you know for sure it won't work for the entire thing. So in this case, 1, 1 is not a solution to the system. But it is a solution to the first equation. So they are only asking if it's a solution to the entire system. Let's continue. Solve this next example by graphing. Let's take a look at how to graph each one. When you solve by graphing, you're basically graphing both lines and seeing where they intersect, because the intersection points are the points that are common to both equations. Alright, how do we graph x equals 0? Well, that's an equation with every single x value being 0, and y values can be anything, which that actually gives us the y-axis. Now, if x equals 3, similarly, all the x values have to be 3. So we've got this line here. Do those lines ever meet? They don't. Since they're parallel lines, they have the same slope, an undefined slope. You would say that there is no solution, because you will never, ever, no matter how hard you try, find a point that works for x equals 0 and x equals 3. Can you think of a point where the x value is 0 and 3 at the same time? Let's take a look at the next example. So let's solve the first equation so that we can graph it easier, and that's if we solve it into y equals mx plus b format. All we need to do here is divide all our terms by 2, and we'll have y on its own. So we'll have 3 over 2x minus 3. And this one here, let's solve it for y. And I'm going to do that by adding y to both sides and subtracting 3 from both sides, leaving us with y equals 3/2 x minus 3. You can just divide that in your own way if that wasn't quite what you would have done. Hey, wait a minute. Doesn't that look like the exact same equation? Of course it is. Since it's the exact same equation, we can just plot it, graph it. Starts at -3, goes up 3 over 2. And the other one would be graphed exactly the same. So in this case, we want to express that all of the possible points that work for both of these equations are described by this line equation. So our solutions satisfy the line equation, and pick one of these. It doesn't matter which one you choose. I'll just pick the first one. So that tells you that there are an infinite number of solutions, and all of them satisfy the following equation. Let's take a look at this example. We can solve the first equation by subtracting 1/3 x from both sides, leaving us with y equals -1/3 x plus 7. The second equation we can solve by adding y to both sides and adding 4 to both sides, leaving us with y equals 2/3 x plus 4. In trying to graph the first equation, you'll notice we have to start at 7. The original grid here didn't go up to 7, so I had to split it up into smaller pieces so that we could see 7 on here. But this gives a very important point about solving with graphing, because when you're solving with graphing, you can imagine that sometimes your grid won't work for your numbers. It might be really big or really small. You also might get an intersection point that falls out of grid points, and how do you find the exact value of that? So there are some limitations of graphing to solve these systems of equations, and therefore we will work towards other methods that involve algebra, which will give us exact answers. But for now, graphing gives us a very good intuition of how we're actually solving these. So, the first one, let's start at 7. 2, 4, 6, 7. And we're going to go down 1, right 3 according to the slope. Down 1, right 3. Down 1, right 3. Down 1, right 3. Or up 1, left 3, up 1, left 3. So those points will connect to make a line. And the second equation will start at positive 4 and travel up to right 3. And you can already see exactly where they're going to meet. Up 1, up 2, right 3, and so on. So that will give you approximately that line. And this will give you this line. However, in this case, you can already see that the common point here was 3, 6. And therefore 3, 6 is the single solution for this example.